Cool. So, hello there. We're back for another day of Advent of Code. Today is day 12. Um, yeah, so it's been a really fun 1.5 weeks so far. I'm really looking forward to today. I'm in a different setting today. I'm actually working out of my office because I've been here late today. Um, yeah, other than that, nothing really else to report. Um, what am I doing? Like reporting about my life? I don't know. Okay, but here we go. The day is about to start. So let's get going. Day 12, passage pathing. Okay, looks like some kind of graph problem. I'm just going to take a quick look at the input. Okay, so definitely looks like some kind of graph problem. With your submarine subterranean subsystem subsisting suboptimally, okay, the only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path, the only way to know if you found the best path is to find all of them. Fortunately, the sensors are still mostly working, and so you build a rough map of the remaining caves, which is my puzzle input. For example, this. Okay, so there's uppercase and lowercase. This is a list of how all of the caves are connected. You start in the cave named start, and your destination is the cave named end. An entry like B-D means that the cave B is connected to cave D, that is, you can move between them. So an undirected graph. So the above cave system looks roughly like this. Your goal is to find the number of distinct paths that start at start, end at end, and don't visit small caves more than once. There are two types of caves, big caves, written in uppercase, and small caves, written in lowercase. Let me just take a quick look. Okay, so the whole name is uppercase or lowercase. It would be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting them multiple times. So all paths you should find should visit small caves at most once and big caves any number of times. Given these rules, there are 10 paths through this cave system. Okay, so we just work through some of these examples. Start to A, to B, back to A, to C, back to A, to end. Okay, note that in this cave system, cave D is never visited by any path. To do so, cave B would need to be visited twice on the way in and back, and since cave B is small, this is not allowed. Here is a slightly larger example. There are 19 paths through it as follows. And finally, this bigger example has 226 paths. How many paths through this cave system are there that visit small caves at most once? Okay, so some kind of graph searching problem. So we need a way to mark visited nodes. Okay, so first thing is we need a way to mark visited nodes. Oops, we're on day 12. The second thing is we need a way to track our path, our current path. We also need possible nodes, outgoing nodes. So this is going to be some kind of breadth first search, I think. So there are two ways. There are a couple of ways anyway. There are a couple of ways to represent graphs that I remember from my comp sci days. One is an adjacency matrix, but I don't think I really know how to use that. Like, it's been too long. The other way is you can keep track of a list of nodes or a set of nodes and a set of paths. Another way is to keep track of a set of nodes, and then each node has a list of all the other nodes it can visit. Which actually sounds like the best way to represent it. So what I want is nodes is going to be a map of, let's see, the name of the node to, I think it will have to be a struct. It will have to be a struct because I want an easy way to keep track of whether it's a big cave or a small cave. Yeah, I want a way to keep track of whether it's a big cave or a small cave, I think. So we'll call a type struct cave. We'll just put name in there just to be complete. I don't know if we'll actually end up using name. We want big, which is a bool, and we want caves that it connects to. So what would be a nice name for it? Caves dot out, caves dot connected, caves dot other next. Caves dot I just call them paths. No, that's such a bad name. We just call it other caves. Nope, but these are strings because these are going to be names. Yes, those are going to be names. So I'm going to work with this basic input first and start with this and work my way up just to make sure I've caught all the edge cases. Let's so we have all this. How do we turn this into how do we turn this into a node of caves? For each, we'll call them edges. For each edge in the data, we're going to use scanf this time. So we're going to call them just A and B. Fimp.scanf. Let's see, string. That's not helpful. So the string is edge. The format is s-s. I don't know if I can do that actually. I'm just gonna play it safe and split it on the hyphen. What's going on? Here we go. Split edge on the hyphen. If nodes okay equal nodes, the first one not okay, then say other zero values okay. Yeah, okay. Then nodes sp0 dot equals a new cave with the name of itself with a big of, we need to calculate this, and with a other that starts with the other cave in it. Yep. So big, we just need to work out what big is. And big is going to be if, we'll do this the hacky way, if the start of the first letter is less than a, lowercase a, I think. In fact, because it's just one line, I can squeeze that in here. Otherwise, it exists, and so we just go nodes sp0 dot other equals, we append the other cave to it. Okay, I think, I'm not sure what this message is, but I'm thinking something like this might help. Cool. So I'm just going to, I think there was a problem with having static fields in A, not static, having a non-pointer fields, non-pointer values in a map. Okay, so already we've hit a problem. In this list of things, only capital A and lowercase, only A and B are on the left-hand side, and C and D are only on the right-hand side. But because this is an undirected, graph, I'm running into problems. So what we're going to do here is A is going to be sp0 and B is going to be sp1. I'm just going to change these around. So A is this, A is that, and this is B. Here we do this, and then we do the same thing. But we also need to swap this around and do it again. A, B equals B, A. I forget you can do this in Go. So now we should have, it's a little, you can't quite tell because these are all still pointers, but at least I see A, B, C, D, end, and start. I'm just going to print out nodes, let's say capital A, and see what we have in there. So A is a big cave, which is good. That's true right there in the middle. It says A is a big cave. It's called A, and it links to start, C, B, and end, which is great. I'm going to check B. B is a small cave, good. And it links to start, A, D, and end. So D should be a small cave that only links to B. C is a small cave that only links to A. Good. Start is a small cave that links to A and B. And end is a small cave that links to A and B. Okay, so now I have a representation of this graph in my memory that I can relatively easily maneuver my way around. Maybe I shouldn't call this nodes. Maybe I should call this, let's call this caves, just to kind of stick with the flavor. So how do we navigate this cave? We have these things we need to keep track of visiting a thing. So breadth first search is what seems the most natural way to do this. We need to keep track of our current path and potential future paths as well. So I'm going to put this into a separate function because I'm not quite sure how I might write this. And I think I might I'll probably want to return a list of paths. This might not be a list of strings. This might be a list of strings. That's probably a better way to do it. So start is going to be start. No, Q is going to be, we're going to start with just the start. paths is going to be this list of strings. And we need to keep track of visited for each like individual thing. I just realized what this means is that none of these graphs will ever have two capital letters. We'll never have a capital cave linked to a capital cave. A big cave can't link to a big cave because otherwise you just keep going around in circles, right? So, and I'm sure the input will just make sure that that's the case, that a capital letter cave never links to a capital letter cave. Yep, which makes sense. So we don't have that edge case to worry about. So a normal breadth first search, but we want to find all the paths, which is where this thing becomes a little bit tricky. I think what this means is that every path needs to keep track of the path so far and all the visited nodes for the current path so far. So I might need a helper struct here. Let's call this path. And then we'll call it, these are not the best naming. We just use bool. It's a bit easier to use with bool. So what goes in queue are these paths, and we start off with a path of, let's see, start, and that's just an empty map. Do I have to name these? No, I have mismatched brackets somewhere. Right. Okay. What this also means is I need a way of copying a map. Sorry, I'm just pulling up the package docs. Does copy maps? No, it only copies slices. Okay, I just need a helper function here to duplicate a map. Now we'll do this thing where we name the output variable, so it's a little bit shorter. Key value in A, out key equals value, return out. So for each path, we start with start. So while, which is a for, queue is not empty. We pop the top one off the queue. The queue, we get rid of the first thing in the queue. So that's just do it, get rid of, like, so you don't have to worry about it, right? I've popped the first element off the queue. I think what we do is then for each cave in cur dot, no, so in caves cur dot path, the last element in the path, this is starting to get a little bit long. In that dot other. Okay, so we should probably pull that out. Cave equals this, right? So the final element in the current path. So for every other path, what we want to do is we want to say we have now visited this node that we're in. Yeah, and I think we can do this at any point, but we've now visited the current node that we're in. New visited is copy visited, new visited the current node. If if the current node, if cave dot big, we don't do anything. So if the cave is not big, then new visited. I realize that this is repeating a bit of work, but it's okay. New visited the current node is true, right? If we're not in a big cave, then now we've visited the small cave. We don't want to visit it again. Now for every other cave, we also want to copy the slice actually. Do we want to copy the slice? I think we do. I'm not sure, but I'll copy it anyway. Nah, that actually needs to happen for each one, doesn't it? New path equals new equals append. So I'm just doing all this copying just to make sure I'm not stomping over any shared data, because maps are a shared resource, are a shared thing. Slices are also backed by like shared arrays, and I don't want to accidentally overwrite some, like reuse some wrong things in different slices and things like that. I'm just not 100% sure of the semantics of slices in Go, which is why I'm just doing this to be doubly safe. Right, so we have an extra thing here. If the other cave, this is the other cave name, right? So caves, cave dot, right, cave. Cave is the name of the other cave. If cur dot visited the other cave, we continue. If we visited it, we don't want to do it. We don't want to go into it. Otherwise, we want to go into it, which means we now append that cave to the new path, and we append into the queue a new path, which is going to be new path and new visited. And eventually, we also want to do another thing here. If cave dot name is end, then we want to append the current path to paths and no more queuing. So paths equals append to paths, the current path, because this would be a path from start to end. And we continue. At the end here, we return out paths. Okay, so this is kind of a little bit the moment of truth. We're going to navigate through our caves system, and we should theoretically get this first set of paths out of it. Or it will either crash like this on line 104, line 72, line 104. Okay, so it turns out I needed to do this anyway. So forget about that. I do have to explicitly initialize it. I'm noticing extra spaces in this output. I don't know if that matters, but let's see. We have start A end. Wait. I'm just gonna print this out a little nicer. And range that. Print out the path like this, so it's just a bit easier to read. So we have how many 10 paths in the system? Oops, print the length of number of paths. 10 paths. Does it look right? Start A end, start B end, start A B end, start BA end, start BA end. Good. You know what? I'm just going to sort these so it's a little bit easier to read. I'm also going to do it like this so it's a little bit easier for us to compare. Cool, just got some type issues. So I do have empty elements, which is strange. Wasn't expecting empty elements for sure. Don't know where my empty elements are coming from. That's so weird. Like it's working. A B A C A N A B A C A A B A A B A C A B A A C A B A C A B A C A B A and B. Wow, that was a mouthful, but came out right. Cur.path. I'm just so confused by the extra element. Is my copy not right? Like, does that actually break it? Okay, I have no idea how this copy thing works. Okay, whatever. Okay, so that looks right. I'm gonna check the second set of inputs, and we should have 19 paths as follows. So we're going to check this real quick. 19 paths, looks right. We have 19, good. I mean, that looks pretty good to me. I'm gonna check this bigger one that has 226 paths. .226, so which means I'm now happy to use my actual input data and get 4,378 paths. Got it, nice. Okay, let's move on to the second part. Part 2. After reviewing the available paths, you realize you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times. A small cave can be visited at most twice, and the remaining small caves at most once. However, the caves named start and end can only be visited exactly once. Once you leave the start cave, you can't return to it. Once you reach the end cave, you must end immediately. Now, the 36 possible paths through the first example are this. Okay, so I think the most straightforward way to do this, I'm going to switch this back to my initial input because that's the only walked through example that we have. I think the way I'll do this is in here, I'm just going to keep track of in my navigate function, visited small twice. I'm going to say that's false, right? And then just the first time you visit a small cave. Oh, you can't even do it the first time you visit a small cave. Oh, that's so hard. Because like, okay, so what I'm thinking, right, is I was gonna say if I was just going to say the first time you visit a small cave twice, you're done. You can't go back to the cave. Actually, maybe it will work. But I was just thinking like, you know what, maybe it will work. Maybe it will work. Visited small twice. And this doesn't actually go here. This actually needs to go into my path. So this needs to be visited small twice is a bool. So it starts off as false, like this, okay? And then just the first time you visit a small cave twice. If cur equals cur dot visited, right? Here we say if cur dot visited small twice is false, okay, no, if you have visited small twice, you continue. If you haven't visited small twice, then so keep track of that. Then the new visited small twice is going to be true. And we're going to use new visited small twice, which means we're going to propagate the existing value through. I think this should be enough, but I'm just not 100% sure. Okay, if this gives us the right answer for this one, 63, 103, yeah. So we're missing some cases where, what cases are we missing? Oh no, there are 36 possible paths through the first example. So do I have duplicates or what? Ah, start and end. I'm going back to start. Hang on. So start. If cave equals start or cave equals end, although I don't think we can actually get to a cave equals end here because we have that check up the top already. 36. Okay, 36 examples. Okay, so this is working. This is working. So all we had to do was just keep track of whether or not we'd visited a cave twice during this current run, and allow the first time to visit whatever cave we reach. I was afraid that was going to not, I'll explain this afterwards, but I was afraid that there was a case where it wouldn't work. The slightly larger example was 103. So I'm just gonna check through all these because I feel like I should do my due diligence here. 103, 103, 3509 for the next example, 3509. 3509, which means I'm happy to run this on my actual data set and get 133621 and get my gold star. Cool. So what I was afraid of was I was afraid that I'd get stuck on, for example, ABDB end, but then I would miss I was afraid I'd miss a case where you only manage to visit the first cave twice, but you can't visit the first cave once and then the second cave twice, if that makes sense. But I realized that that doesn't matter because of the fact that I'm doing a breadth first search. There is always going to be an existing path in the queue that skips that first double visit. Now, it's a little bit hard to explain, but if you walk through the code, it makes sense. That it won't just get stuck on visiting the first cave twice. So you see here, for example, you have this case where it visits C once and then B twice. Now I understand that if you really look at the graph, it's impossible to visit C twice. Actually, no, it's not impossible to visit C twice. You can go AC, ACA, right? Yeah, you can go AC, ACA. So I was afraid that you would always do, say, for example, AC, ACA before you go to B, and then you can never end up doing AC, AB, AB. But actually, because of the way the breadth first search works, that doesn't happen. You end up exploring all possible paths, even with this constraint. And so yeah, that's probably the only thing I have to comment on this one. Knowing about how graphs work, basic graph algorithms like breadth first search, which is what my queue here is. This is a breadth first search, but it's a breadth first search with kind of keeping more information about your current path, and not just, for example, the path, but you also have to keep track of nodes you'd visited. You also keep track of, in the second part, whether you'd visited a small cave twice. But you can encapsulate all that information in your breadth first search and then keep going. And then just with my specific implementation where I did this overly cautious and pedantic copying of my information, I used the code in Scala, and in Scala, all of these data structures would be immutable. And that would mean that I don't have to do this copying because I know that every time I append a new element, I'm getting a new object back, and the previous object remains unchanged. And I'm not 100% sure on the semantics of Go, but I do know that with slices, you sometimes get really interesting behavior with slices, where let me just do this. Cool. I just do know that you get this really weird behavior with slices where, say I have A is this, right? And I say B equals append to A B. If I print A and then B, what do I get? Okay. It's not the weird thing that I thought would happen. What if I did this though? I pre-give it extra space like this. Okay, no, my fears were completely unfounded. I just felt I came across a weird instance where modifying the okay, no, this is what I was thinking of, I think. This is what I was thinking of. So maybe it wouldn't have affected this specific algorithm. But say I have an array A and array B, and B is just is just B appended to A, right? But what if I change B0? What would you expect to happen? Which is a good question here. And I think what happens is that A, because B shares the same underlying slice as A, that both A and B will change. Okay, no. What if I changed A and not B? Okay, my fears are completely unfounded. I was sure that there is some edge case behavior, something like this, where these sorts of things can happen. So I can't reproduce the exact case where this would happen. Okay. Now I have reproduced the case where this happens. And if I do this, same thing. Okay. So this is one of those gotchas of Go. The reason it happens this time is because I've pre-allocated slice A to have a capacity of 2, that's this 2 here, but only one space. So what this means is when I append to the slice A, it doesn't have to reallocate the array because that backing array already has capacity of 2. It's just limited off to 1. So B is now actually reusing the same underlying array as A, which is why when I change index 0 of B, it changes A as well, even though I've never written C into the array A at any point. And the same thing, if I write into A, because it shares the same underlying array, these two slices, B changes as well. Now, it didn't happen when I had it like this. And the reason it didn't happen when I had it like this is because the capacity of this slice at the top, the backing array of this first slice, is 1, not 2. So when I append to this slice, Go has to, behind the scenes, allocate extra memory, which means it has to allocate a new array. It copies everything from A into a new backing array. So A and B, so slice A and slice B now refer to different backing arrays, which is why you can change one without changing the other. But if there was enough capacity, then the two slices refer to the same backing array, and changing one will change the other, which is a really, really dangerous gotcha, if you ask me. But it is more efficient. And so this is one of those edge cases that you really have to be careful of when it comes to these sorts of lower level mutable data structure languages. And I didn't want to have to deal with this. So I did have to do a little bit of digging to figure out the actual edge case where this would come up. And in my case, I don't think I was ever back in the algorithm for today's challenge. I don't think I was ever actually changing anything in the backing the path, right? I was just always only appending to that array of the caves. Oh, not that one. This one over here, navigate. I was only ever here appending the new cave to the path. So actually, I think I would have been okay without this extra allocation and copy, but I just didn't want to have to debug something that went wrong in that case if something went wrong here. And so I decided to just be extra safe for the purposes of programming this thing and copy the slice. That's actually a really serious thing to be careful of. And I do know there is an article on the Go blog that talks about this behavior. So something good to know about if you ever plan on actually doing some low-level coding in Go, that different slices can refer to the same backing array, and changing one will change the other if the backing array is the same one. And it's kind of hard to know, especially if you've been appending things to slices or slicing them with the colon syntax, like which backing array each slice is using. Yeah. So really fun problem with graphs. Yeah, nothing much more to say. Thanks for joining me today. We had a lot of fun, and I will see you again tomorrow.